Boom. What's up, everybody? Today, I want to ruin the way you think about literally every living thing you've ever looked at. And believe it or not, the rabbit hole started because I was in the middle of killing a fly. Not usually the beginning of a scientific revolution, I know, but I rolled up a magazine, boom, take him out. Boy, I hit that Goku when we started doing the Ultra Instinct. You know, in that time that he bought, I started thinking, I'm like, I wonder if like they have any emotional responses. Like, is he scared right now, or is he just a calculated machine? You know, like what's the thing? You know, like what's the deal? So that led to this, and basically, I call this translatable intelligence. It's different species being able to intelligently decipher the emotional responses and displays and the communicative actions of another species, like humans and dogs having a relationship. You know, or like how, if you ask me, it's like a scale. I feel like the bigger another organism is, the more easily a human could translate its intelligence and emotional responses.
Though that's not always the case.
When I say that's not always the case, I'm talking about how there are like extreme outliers for certain species of animals, like the bear I'm about to bring up, because I'm listing animals, but I cut it at the bear to make a point where basically, you know, there's a difference in bears that have been in captivity at different lengths of time, and depend on who their caretaker is, what they're teaching them, what they're exposed to, stuff like that. And then all of that big group compared to a wild bear that's like never seen a human or rarely sees them, and probably rarely ever even sees other bears. And that's why I say what I'm about to say about the bear. But then that turns into something else that shows it's not about size also, because you can have animals of different sizes with different experiences. And this also ties into the shared culture between humans and different upbringings, different experiences, you know, how traveled you are, how involved you are when you travel. You know, all of that contributes back to what makes you the individual that ends up doing everything you do, you know? Well, nothing bears will surprise you, man. A lot of animals will. I mean, it's deep. But I feel like, you know, the bigger it is, the easier it is. The smaller it is, we can't hear them the same. There are octaves we're missing. There's a whole quick, subtle way of moving that we're not used to, or that we won't even catch, and then it gets smaller. Like, you know, you're talking about like certain types of, you know, rodents to bugs, flies. So basically, like, look at reality as like a radio station. Like, I mean, not a radio station. Stuff that radio stations and TV stations catch. It's part of this electromagnetic sea. And basically every existence for an organism is a radio station. And sometimes something is so deep in that other world on the way to becoming microscopic that it's in a whole another universe in a way to where it's like watching an interdimensional cable. You know, like how they do on Rick and Morty. It's you don't catch those stations. It's in another world, you know? Like, and it's like that with everything, every piece of existence. All the frequencies, languages, songs. But sometimes they can overlap, and that's where the whole translatable intelligence thing comes in. And that could even like go to like different cultures, racial backgrounds, upbringings, disciplines of martial art. Like, it's crazy. Yeah. But yeah, so let's get into it, man. For instance, what color is the shirt? This shirt is blue. But there's no such thing as blue, or red, or green, outside the brain. The colors don't exist, but they are different wavelengths of light. And your brain turns invisible electromagnetic energy into color. It's basically like running Photoshop in real time, you know? It's like we're always predicting things before they're actually even happening. Our brain is so fast with time traveling every time we think, for the most part. And like a bee wouldn't notice this blue shirt, but it might notice ultraviolet reflections that I literally can't see. Just like a snake doesn't really just see a mouse, it sees the heat. And the birds see ultraviolet markings that are hidden in feathers that humans completely miss, you know? And it's the same way bats could build a picture of a cave using echoes, you know? It's like biological sonar. We all got different hardware and software, you know? And it's like, so who's really seeing reality? We all just translate it. But then I started thinking that, you know, maybe intelligence works the same way. You know, it's just translation. Like, think about language. If somebody's speaking Mandarin and I only speak English, it don't make me less intelligent. Like, I just can't translate my intelligence, you know? I know a little bit of Mandarin, a little bit. My studies had got cut short, but And a cow ain't a bad monkey, and an octopus ain't a weird dog. You feel me? It's just different operating systems. It's crazy. But then I thought about something else, and I'm like, the bigger the animal get, the more we tend to feel like we understand it. Like when you think about it, people usually feel more connected to an elephant than a mouse. Some more connected to a mouse than a lizard, more connected to a lizard than a fish, and more connected to a fish than a bee, and more connected to a bee than a fly. Which goes back to what I said earlier, remember, about the size not really mattering because you could have different species with different experiences contributing to different planes of intelligence. And somewhere down there, we stop thinking about feelings altogether. Like a bacteria, we don't even hesitate, But why? Is it because bigger animals are always smarter? No, not really. Not even close. If anything, none of us could compete with the intelligence of a bacteria. That's what's crazy, but they're so simple. Not even the nervous system. It's crazy. And some birds can solve problems that many larger mammals can't. Octopus have evolved astonishing intelligence despite being much smaller than whales or elephants. So size isn't the answer. It's just part of the illusion. What size often changes is how much of another creature's life we can recognize. I started calling this translatable intelligence. Not because I think intelligence changes, but translation changes. Like when you think about what happens as an animal gets larger and develops longer lives. Their childhoods often get longer, they play more, they learn more from experience, they spend more time with parents, they build more complicated social lives. They recognize individuals, they mourn, they teach, they cooperate for years, and they even have cultures that get passed from generation to generation. Now suddenly their lives start looking familiar, Not because they became human, but because the overlap got bigger. Think about dogs. A dog gets excited when you come home. It learns your routines. It gets jealous. It wants attention. It plays. It gets scared. It learns your emotions. Now ask yourself, did the dog become intelligent, or did enough of its inner world overlap with ours that we finally recognized it? Now imagine explaining jealousy to a dragonfly. Maybe it has experiences we can't even imagine. Maybe they're real. Maybe they're important. But maybe almost none of them can translate into human language. It's not a lack of intelligence. It's a lack of overlap. Now here's where it gets even crazier. Scientists increasingly think your brain isn't waiting for reality to arrive. It's predicting reality. Your brain is constantly making educated guesses about what it's about to see and then correcting itself when it's wrong, which means you are not watching reality. You're watching your brain's best live reconstruction of reality. Your entire life has been beautifully corrected prediction. Now combine that with different animals. A fly's nervous system updates visual information much faster than ours. That's one reason they're so difficult to swat. To you move your hand instantly. To fly, it may have had much finer slices of that motion to react to, just like a phone with higher resolution. Same event, different refresh data. A hummingbird's heart beats over 1,000 times a minute. A whale's heartbeat can slow to just a few beats a minute while diving. Imagine if your thoughts, emotions, and perception all rode on those different biological rhythms. Maybe every species isn't just living a different life. Maybe it's just living a different tempo, And here's the part that really broke my brain. What if intelligence isn't one dimension? Like what if it's 6? Sensory bandwidth. What can you detect? Temporal bandwidth. How fast do you experience change? Behavior bandwidth. What can your body actually do? Social bandwidth. How much thinking happens between individuals instead of inside the brain? Developmental bandwidth. How much can an experience rewrite your brain over your lifetime? And emotional bandwidth. How rich and varied are your internal states? Now stop imagining a ladder, start imagining a map. You feel me? Humans aren't standing at the top. We're standing somewhere on it. Dogs are somewhere nearby. Dolphins are nearby in different directions. Octopuses are way off there. Bees are somewhere else entirely. Fungi might be so far away we don't even know where to put them. The question stops being who's smarter and starts becoming who's speaking the language I can understand. You feel me? And that changes everything, because suddenly a reptile learning to trust its owner isn't weird. A fish recognizing the person that feeds it isn't weird. A crow remembering a human face for years isn't weird. Those aren't animals becoming more human. Those are moments where two completely different worlds briefly overlap. Yeah. For just a second, 2 radio stations come in clearly. So, should you feel bad for killing a fly, honestly? I don't know. I'm not the scientist doing the research on that at the moment. But there are scientists who are doing this currently, and I'll go over some of their work, the experiments they're doing, and whether or not I think it's conclusive, and to what, So, all right, first we have Lars Chitka, professor at Queen Mary University of London, spent decades studying bee intelligence, author of the book The Mind of LB, which summarizes most of this research. Clint Perry, who worked on famous bumblebee ball rolling experiment, where the team observed bees voluntarily rolling balls with no apparent reward, leading them to argue the behavior met the scientific criteria for play. And I'll go over what they did in a little bit and how I feel about it. There's Andrew Barron, uh, studies insect brains and insect consciousness. Um, he has argued that insects may possess a very simple form of subjective experience because of how their brains integrate sensory information. But I mean, a robot can do that. Colin Klein works with neuroscientists on the philosophical side of consciousness, helping develop ways to think scientifically about consciousness in non human animals. And we have Mandeep Bains, who co-authored research on the optimistic and pessimistic behavior of bees, something else we'll go over also. Geraldine Wright, who helped conduct experiments on bee cognition, learning, and emotion-like states. And also, last one, William Gibson, researches persistent defense states and fear-like behavior in fruit flies. This research is funded by national science foundations, universities, government research councils, European Research Council, Biotech and Biological Sciences Research Council of UK, Australian Research Council, and private scientific foundations. And these studies are generally published in peer-reviewed journals like Science, Nature, Current Biology, and Proceedings of the Royal Society B, and Current Opinion in Insect Science. So basically, these are how the experiments went. Number one, optimism and pessimism in bees. The experiment was done with scientists training honeybees to associate different smells with rewards. So there's one odor, which is sweet sugar water, and there's another, which is bitter quinine water. Smell A, good. Smell B, bad. So they divided the bees up, two groups. Boom. Group two, they were given an unexpected sugary reward. So the bee's brain released dopamine and other reward chemicals. Immediately afterward, researchers presented the ambiguous smell, something halfway between good and halfway between bad. And instead of avoiding it, the rewarded bees flew toward it, and the bees that didn't get the reward, they weren't, they were basically indifferent toward the smell. So this proves that the bees that got the reward were behaving optimistically. So they say it's an optimistic cognitive bias. And this is supposedly the same kind of cognitive bias that is seen in dogs, rats, pigs, monkeys, and humans during clinical testing. Um, during these types of experiments. And so they induced stress instead of sugar, and the bees, the reward transmitters dropped dramatically. So then they repeated the ambiguous smell test, and instead of investigating, they avoided it. Basically, like them, building a pessimistic cognitive bias now, saying, they learned from their experience and they don't want to experience that again. And still, if you ask me, that doesn't necessarily say they're having the same experience as us, because any reaction from the nervous system can't be generated without the chemical feedback loop, the response, sensory input. It's like I said, a robot can do this. You don't have to be alive to experience any of this stuff that we're talking about right now. But doesn't say anything about how I feel about the insects, because we're going to get into all of that later. I'm talking about from the scientific perspective right now, because I'm the one who didn't want to kill the fly. Remember that. Um, Hold up. Let's see. All right, now here's the experiment about the fear in fruit flies. And supposedly it's become one of neuroscience's favorite model organisms because their nervous system is relatively simple but genetically accessible. So, when repeatedly exposed to a lumen predator-like stimulus, flies show persistent defensive behaviors like freezing, escaping, heightened vigilance, and avoiding previously neutral locations. These responses can continue after the immediate threat has disappeared, indicating an internal defense state rather than a simple reflex. Researchers describe these as emotion-like states, though they stop short of claiming they are identical to human fear. So the giant shadow experiment that they did, they put a giant like disc over the flies, and to them supposedly it looks like a bird diving, and the flies become hyper alert, and even after it disappears, they remain cautious, and they say this resembles persistent fear rather than momentary reflex. And as far as the internal state goes, the researchers found the flies' behavior depended on previous experiences, hunger, fatigue, and recent threats. And the same exact stimulus produced different reactions depending on internal conditions. And they say that's remarkably sophisticated for an animal with roughly 100,000 neurons. I mean, I don't know. We'll get into what I think in a little bit. One misconception is that insects have completely different brain chemistry, but actually, many of the major neurotransmitters are ancient and shared across animals. Insects use dopamine, serotonin, ah, GABA, glutamate, and acetylcholine. These chemicals evolved hundreds of millions of years ago, and they don't produce identical experiences across species, but they regulate learning, motivation, mood, movement, and decision making in insects as well. So, dopamine in humans regulates motivation, reward prediction, movement, and reinforcement learning. In insects, it regulates learning, reward, motivation, and decision making. Serotonin, humans, mood, anxiety, appetite, sleep. Insects, aggression, feeding, locomotion, social interactions, and behavioral flexibility. Different nervous systems, same ancient molecular toolkit. Do insects feel pain? And that's one of the biggest questions. Uh, nociception, detected of, detection of harmful stimuli. An example is touching something hot, your body pulling away. Like I said, and they just said it, even robots can do this. Pain requires an unpleasant subjective experience that is much harder to prove. So the researchers have found insects can detect injury, protect injured limbs, groom wounds, and reduce activity after injury and remember dangerous experience, and they can even trade off pain against reward. But it still doesn't prove anything. And with the playing with the balls, so they had one route that went straight to food and another that was covered with small wooden balls. The balls gave no nectar, pollen, shelter, or mating opportunities at all, but some bees repeatedly left the efficient route to roll around the wooden balls, sometimes dozens of times. And they even noticed that the younger the bees were, the more times that they would do that with no reward. So to them, it indicates a state of play. But then when I see the picture of the balls, I see that, they're painted bright orange and purple. So I'm like, would they go to them if that weren't the case, if they weren't attracted by the color? Would they still recognize it as something that they could play with? When I see, like, every once in a while, they have one non-painted ball, one just, brown wooden ball. But I'll have to look deeper into a lot of this. And oh, they said males played more than females. And says the bees preferred places with the balls that even didn't have food. And I don't know, you never know what this is about. Not that I say it's not possible. Let's see. So the New York Declaration on Animal Consciousness, uh, 2024. It was signed by hundreds of scientists. The declaration does not claim insects are definitely conscious, but it says that there is a realistic possibility that many animals, including insects, crustaceans, mollusks, and other invertebrates, have conscious experiences, and that evidence is now strong enough to warrant ethical consideration rather than dismissal, which is awesome, and I like it. Why this changes biology? Um, because they used to assume large brain was the only way of having high intelligence and consciousness. But now new scientific research is turning that on its head. It's crazy. But there are still a lot of specific questions I have, and we get deep into like the specifics of the experiments and what they have not done yet. And so, all right, for the wooden ball experiment, my color question. So they used yellow balls and purple ones, and the question is, would they still roll them if they were gray, transparent, and if they were like different textures, and if they didn't resemble anything at all that they naturally encounter. So they haven't done that yet, but they've answered to those questions saying, oh, there was no food inside the balls, and rolling them delayed getting food rather than helping, and about the whole younger bees and all of that, which that's common signature of play in many animals. And yeah, that's cool and all, but I don't know. I want the proof of something like loving something, just to prove a point because I believe it's possible. Let's see. Oh, and like I said, the neurotransmitter argument, and it's one of the best ones because the nervous system is nothing but chemistry. You know, it tells us how behavior changes, not whether there's a subjective experience behind it. And as far as the love question goes, it's probably the hardest thing right now. If an insect could truly love, they expect behaviors that go beyond instinct or immediate reward, such as preferring a specific individual even though there's no reproductive benefit, or sacrificing resources repeatedly for that individual, showing distress when permanently separated, or changing future behavior because of the relationship, rather than genetics or conditioning. And right now, they don't have any convincing evidence that insects can do this. But some insects recognize nestmates or colony members, and many social insects cooperate extensively. But those behaviors can largely be explained by evolution, kin selection, pheromones, colony level organization, and none of it demonstrates an emotional equivalent of human love. So right now at the moment, that's where we're at. But that's only because, like I said, I'm not the scientist doing the experiment. No offense. Maybe it's just like about humility. I don't know, man. I believe that every living thing experiences reality through its own translation. Then the most arrogant thing humans ever assumed is that our translation is the know all, be all, or whatever. But intelligence isn't about climbing higher. It's about discovering just how many different ways there are to experience one universe. And maybe the closer we get to understanding those other translations, the closer we get to understanding ourselves. That's all I got for right now. So I see y'all on the next episode.